Hello, Assalamu alaikum. Welcome to the fourth lecture of design and implementation of RISC-V pipeline code. In the previous lectures, we have gone through how we have designed the decode cycle of the pipeline stages. And today, the main topic of our lecture will be the implementation of the execute cycle. So today we are going to see that how we have, what components are involved in the execute cycle and how we are going to code it. So the procedure is exactly the same as of the previous lectures. First, we are going to go through the theory and then we are going towards the coding part. So let's start with our theory topic. First, we have to make the, let's see how the execute cycle part consists of which of the following circuitry. So the modules have been, which are going to be used in this execute cycle are number one, the AND gate, which is responsible to find out whether are we getting a branch instruction as a valid instruction or not. And then we have a mux, which has a user selector for our source B, ALU source B input. Either we can have the source B from the register or from the immediate value, extended immediate value. The third module is our simple adder, which is used to calculate the branch PC target address. And the fourth is ALU, which is the main responsible for the execution of 80% of our processes. And then we have the fifth execution state register, which are going to be declared as we have done in previous lectures. So let's see I guess the diagram is very much clear that we have already know what these registers have been. We have declared the decode register in the decode cycle part, and we have just assign the register values to output ports, which we have declared as register ID and all of them. So these are all the inputs you can see here, and on the left hand side, right hand side, there's a output register, and those are the outputs, which is indicating that subscript, which states that these are the signals of the memory stage. So, and you can see that I've again put some X marks here because these signals are those signals which have been used already in the decode cycle or in the fetch cycle. So we don't have to worry about them. Here you can see the PC target E, which is already we have been used in the PC fetch cycle. So we don't need to cater that signal as well, but this will become as a output port of the execute cycle without any registering. Here you can see that all of the signals are passed from the register, but here is a feedback part which is out without the register. So we have to make sure that this value is without the register and directly map on the wire, not on from going from any registers and that. So this is a basic theory. I guess we have covered it now, and this is very much straightforward as all of these topics have been covered in detail in the single cycle processor implementation. So let's just move towards the coding part, and we are just going to convert our single cycle execute data part to pipeline data part, right? So okay, so let me close all of these extra files which I have already opened it here. So let's make a new file which will be named as execute cycle.b. Right, so let me open like previously. Definitely I'm going to include my licensing. Okay, so as we know, the modules which we have to include is the ALU. The second will be our simple mux, and there will be a simple adder which we have to add it. I guess there's a PC adder, so let's make it these three, and there's a simple AND gate, so I think we can just use it as a during the coding as well. So first I'm going to include the ALU, and then I'm going to include my mux, and then I'm going to include a PC adder. Right, so let's start with the module declaration module, and definitely I'm going to name it as execute cycle, and then here will be the end node. Okay, the signals which we are going to mention here are definitely first of all we have clock and reset, and then I'm just going to copy paste the output ports from here, which will become as an input for me without any wasting any time. Just let's just copy paste it. Definitely we are going to just compare it again and make sure that we have already mention the correct signals here. Okay, so let's first make sure that all the signals which we have mentioned are correct. Okay, the first signal was register YT, so definitely we have ALU source E. Then we have a memory write as well, all of the registers ports. Then RD1E, RD2 is also mentioned, immediate extension is also mentioned, and we have RDE, PC, and PC plus 4E. So all the inputs have been mentioned successfully, right? So definitely I'm just going to again copy the output form and convert it into the inputs of my execute cycle. Okay, but I'm keeping my practice exactly same. I'm not declaring output right now. We will going to declare them in the end of the designing so that we know which signals we have to use as a output one. Let's just add some comments as well. Declaring IOs, right? Okay, first we have declared IOs, then we do the declaration of interim wires. And then we do the declaration of register, and then we declare declaration of modules, right? So definitely I'm going to declare the modules first, so from that we can know what wires we are going to use, and after that we can know which register which have to be declared here. Okay, so let's first call our ALU unit. A is operand 1. Okay, right, in our result we have ALU control signal. We have some flags here. These flags have been used to carry out multiple which are going to be used in different branch instructions, but we have already going to see the branch equal instructions. So maybe we are not going to use it here, but after you are going to expand your data part, so definitely you have to use this signals, and all of these flags information have been provided in our previous single cycle series. So you can go and have a look at that also. Okay, first ALU, and then I am going to use a simple mux. Okay, so I'm declaring the mux above. So this is an ALU source naming as ALU source mux. Yes. Forget to open. Definitely, we need a small PC header as well, which are going to add a branch target to it. So the third header is not a PC header. Basically, this is a branch header. So, but I've declared it as a header, so I'm going to use that as well. We can also design a new header, but that is no use of it because we have designed a header as in a way that it has two inputs, not a fixed any input. So definitely I can use it anywhere by just changing the inputs in mapping the inputs differently. Okay, so let's say branch header. Okay. Okay, let's see if we have followed our, okay, we have a mux, we have an header, we have an element. Okay, we have forgot to use the AND gate. Definitely the AND gate logic will be implemented directly, so we don't need a any particular declaration of module initiation for it. So let's start with placing our inputs. So first see what are the inputs of the mux. As we can see in the inputs of the mux, we have two inputs getting from RD2 and one is getting from immediate extension E. So these both are the inputs. So definitely I'm just going to connect the inputs to it. One of my inputs is RDE. So it will become A, and I have immediate extension here. And the control line for this mux is ALU source E, so which is definitely one of the input as well. So I'm going to just connect the ALU source E to my control signal. And we have an output here. So definitely I have to declare something output, which is a wire, which we have declared. So let's declare a wire, which will be a 32 bits, sorry. And I'm making it as a name of a source B. So I'm just going to use source B here, connected with here, and definitely the source B will become a part of the B input of my ALU. Right, source RD1 is definitely going to the source A. So I'm just going to connect my RD1E to source A. And then we have a result. So let's wait for it. First, we are going to connect the ALU control. ALU control is the ALU control coming from E input. So ALU control, we're going to map directly on it. Okay, I've just mentioned that these are the flags: overflow, carry, and negative flags, which we are not going to use. So let's just keep it empty. You can add the functionality in future if you want to add some, increase the data part for that. For right now, I'm just going to leave them empty, right? And for the result, definitely I need some one of my wires to which are going to be connected to my register. So let's declare a wire here, which is also going to be a 32 bits, and I'm naming as a result E, which shows that this is the result of the execution stage. And going to connect it with. Okay, and definitely I need a wire for zero flag as well. So wire 0E. And going to connect the 0 vector 0. Right, my ALU has been connected successfully. Now I just have to connect this PCR, so we can know that PCE and immediate extension are getting input to the adder. So both are my inputs. So I'm just going to use PCE, and the third build I'm going to use is immediate extension. Okay, and definitely there will be an output from here, because as we have mentioned already that the output of the adder is not going to any register, so I can declare the PC target as directly as an output port of my design. So let's do that here, PC target E. So this is the first output I'm declaring for my fetch execute cycle state, right? And just going to connect it to the adder output. Okay, so I guess we have covered this PC target E concept clearly. Immediately get input into it. All of these logics have been completed. Okay, now you can see that few things. Let's first come with our zero logic. What we have done that we have branch E is getting AND with our XOR E. And definitely this jump in data part has been also included with the OR gate, but I'm definitely we are not implemented the jump instruction in our data part, so I'm going to neglect that thing. All we have that is the branch E. We are going to end the branch E signal with our 0E signal, which we have obtained right now. So simple, what I can do that I can declare this PC source E as an output signal, right? So let's PC source E, which is also one of my output ports, and it is this output is a single bit output. Okay. So what I can do is simply I can do this using the assign statement here. Not going to do anything. Assignments. I'm just going to assign PC source E as a 0E and with my input signal of branch. So this logic have been completed. Now you can see that all of our logics have been complete. All we have to do is to declare the registers right now. Okay, you can see that right E signals directly coming and going as the output port. Results also get have not used anywhere. It's just an input and output. Memorize input and output. ALU control have been used, so we don't need that port. ALU source has been, we don't need that. RD1 has been used, RD2 has been used, but RD2 has one output port which is going as a write data E, which will be going to as a write data M. So definitely I have to declare the write data M register for it, or you can say write data E register, whatever register you can name it. PCs have been completely finished here, so I don't need that as well. Immediate extension has been completed finished here, so I don't need that. We have an RD which is using as an input and going as an output, and PC plus 4E as well. So we are going to use that. So let's just declare some of the registers quickly. So we know that registers reg write key will be used, right? So definitely as our practice, I'm going to use the subscript here with my reg keyword. Reg write key will be used. ALU source I don't need it. Mem write key will be used with the subscript of R. Result source E will be used as subscript of R. Branch E I don't need it. Control E has been used. Okay, now the other, I guess these are three control signals which have been used, right? There's control. Reg write E, result source, member. Yeah, these three signals will be going further. Else all the signals have been used in this stage. And then we have a register of what we can say RD1. We don't need it. Let's say RDE. We need this. So this will become RDER. Batch of registers. Okay, then I have a register of PC plus 4E as well. Okay, so PC plus 4E. Okay, let's say 1, 2. These two registers have been declared, and 3 is the control signal. So 3, 4, and 5 registers have been declared successfully. Now I need one register for this RT2E and one for my ALU. Right, so I'm mentioning here only RD2E will become my RD2ER, and new register is for result E underscore R. Okay, so these are the registers which are necessary. We have declared the interim registers as well. Interim wires have been used. So now all we have to do is to design our register logic. If we set is the one equals to low, then you have to do the following things. Okay, so just quickly I'm going to these registers. Okay, so we are done with our first logic, and we are going to use our else. Okay, all I have to do is just copy paste it again without any delay. Just going to replace it here. So my input will become my outputs register map. So just I have to remove the subscript of R from here. You have to put it into the quick. Okay, so RDR is not used anywhere without any changes. PC plus 4E is also doesn't have change anywhere, so I'm going to use that as it is. Okay, RD2R is also not used anywhere, so it has been used, but it was also result E. This is what my result ended. Guys, so this is all we have done with register logic, and now all we have to do is to use the assign statements. So definitely I'm going to just, as we did previously, going to use removing and naming this as an M, which makes shows that these are the output ports of my execute cycle and the input port of my memory cycle. Okay, so for the right RD2, I think we have to change the name from write data E, because the RD is named as a write data. So let's change it write data M, and here we will keep again. The reason I've changed the name is to make my naming convention exactly the same, so that we don't get confused in the future, right? And the results, so definitely ALU results. I will going to name it as of ALU result M. Right, so let's just check how many output ports we have from here. So from here you can see there's a 1, 2, 3, 4, 5, 6, 7 output ports which have to be mentioned here. Okay, so let's check it. 1, 2, 3, 4, 5, 6, 7 are correctly the output ports. Two output ports are directly going without the register, which we have already mentioned, the PC source key, and the PC result, which we have directly mapped towards our header. Right, so just have to make these as the output port again. Let's make it quickly. Okay, so we are done with our output post declaration. Now all we have to do is to let's quickly copy and them, so things get a little bit of easy. Paste them here because all of these are single output ports. Here, then from here I have output of 5 bits, which is the RDM, and from here I have an output of 32 bits. Right, so these are my okay. So as let's go towards quickly from here that we have declared our 3 include modules. We have execute cycle, the top module name. We have declared our input and IOs and outputs. Declaration have been done, 10 minutes have been done. We have declared the register as well. We have initiate 3 modules here, which is the ALU mux, ALU, and the PC header. And we have also implemented our register logic here, and we have also used our assign statements. Right, so now definitely I'm not going to make this test bench again this time. It is your one of task to create a test bench for it and run and verify that either you are getting the result correctly or not. The result should be coming after a 1 clock cycle. Wherever you given an input as a positive, so the output should become after 1 cycle, right? So that is task for you. But for right now, I'm just going to show you that when you are going to run a command of iVerilog. So let's see if our design is error free or not. Okay, so here I'm going to execute it. See, okay, so now you can see that we are having some of the syntax error. So let's quickly resolve that at line number 73. Let's see what syntax error we are having. Okay, here you can see I have made a simple spelling mistake. So let's check it again. Okay, now we have lots of error. So okay, oh, okay, clock and reset. Okay, here we have forgot to declare our default inputs, which are clock and reset. See, after running the iVerilog command, we haven't get any of the errors. So it's make our syntax is correctly coded, and there is no error in our design file. So just you have to make a test bench and verify that either you are getting the functionality which you have implemented, that all our results should be getting after one cycle. The result control few of the controls should be mapping directly, and some of the results should be getting from after some operation. Like we could be getting some ALU result on by having some operation on operand A and operand B. It can be add, subtract, anything you have you want the instruction to be performed for it according to the control signals. And those output will be mapped. And definitely if you have a branch instruction, so there will be some output signal on PC source E, and then you are definitely getting some PC target E as well, which has got to calculate by adding a PCE and immediate extension value. So I hope this make the concept clear of the execute cycle, and how we have converted our single cycle execute part to our pipeline version of it, and how we are including the registers. So do verify it on your side and let me know if you are facing any errors. So that is all for today. Stay tuned for the next video. Thank you very much. Allah Hafiz.